Here's a conservation of energy problem here that involves the following. There's a mass here, which is a height h naught above the ground. And what it's going to do is it's going to be released, and this is all frictionless in here. It's going to go ahead and slide down this incline. And it turns out that the mass here at the top here is some distance, we'll call some distance capital A, from where this spring plunger is. So that's how far it is. What will happen, of course, is this orange block here will slide down a distance A, hit the spring here, and the spring is going to slow it down and stop it to the point where the mass is just sitting here against the spring, not moving at all. But of course, as a consequence of that, this block has pushed the spring in. Here's the spring's equilibrium position right here. It's pushed the spring all the way into this position here. In other words, it's compressed it by distance delta S. And so the problem asks for a variety of things here. In particular, I think it just wants to know what delta S is right here. How far would this mass conceivably compress the spring in this scenario here, given that the spring has a spring constant K and some usual things like that. And there's some other parameters in the problem that you might need, but that's sort of a nutshell what it's telling you here. So one of the big cautionary notes about this problem here is that when the mass makes it all the way down to the bottom, it isn't quite on the ground anymore. It isn't quite on the ground. So the ground level is, of course, all the way down here. This is where your potential energy would be 0. This is y is equal 0. But the mass isn't all the way on the ground, so it still has a little bit of gravitational potential energy right here. In fact, it's still a distance, say, h1 above the ground. So we'll have to account for that as we work this problem. So it's straight conservation of energy. I'll just say E initial is equal to E final. And the initial energies that I see here is I see the mass times gravity times h naught. This block has some potential energy as it starts. And then it's, of course, released, and all this potential energy becomes kinetic energy that goes down, it speeds up, then it hits the spring and starts to slow down. And all of the energy that it had up here eventually goes into the spring. So in the final sense over here, we have a compressed spring, 1/2 K times delta S squared. There's a compressed spring. But now don't forget that the box isn't all the way on the ground, so it has a little bit of gravitational potential energy. So I'll go ahead and put an mg times h1 in there. So there's my initial energy, and there's my final energy. So conceivably, this is pretty simple, I guess. Here's the initial energy, here's the two final energies. The spring is compressed, and there's a little bit of potential as it sits there above the ground. But we have too many variables. Like, we don't know what h1 is, and I think we know what h naught is, but there's just too many unrelated variables here. But it turns out they're not completely unrelated. So in particular, if you look very carefully at the geometry, maybe separate it out a little bit and look at the problem geometrically like this. Here's the ground like this. And what we have here is here's sort of h1. That's that height that the block is sort of sitting at when it's sitting there attached to the spring. It's not all the way on the ground. And then you can sort of draw the triangle on top of that, if you will, something like this and like this, where this total distance right here, this is h naught. That's that distance the block was initially before it slid all the way down. So the block sort of starts here and ends here. And what is this distance here on the incline is that it slid 4 meters here, or whatever that distance was in the problem. I think some distance A we're calling here, before it impacted the spring. And then it slid an additional delta S right here, which is the spring impact distance. So see this, the distance that the block actually slid along the incline, slid all the way down with no obstruction, distance A. Then it slid another additional distance, delta S, as it was in contact with the spring. So this total slide distance here is A plus delta S. And of course, this is alpha here. That's that incline angle at the incline right there that we haven't dealt with yet. And if I look very carefully now, I think I can make all these variables sort of come together. In particular, if this is h naught right here, and this is h1 right here, this distance right in here is going to be h naught minus h1. That's this little distance right in here. Now, if I look at the triangle, you can get out of this that the sine of alpha is equal to opposite h naught minus h1 over a plus delta s. So you have a nice relation between all these h's and delta s's and a's and things like that. In particular, if I solve this for something like h naught minus h1, I'll get a plus delta s times the sine of alpha. And I'll sort of leave the problem here, but what this is here is this is sort of the change in the overall vertical height of the block. Remember, it started in h1 above the ground and ended up at a distance h1 above the ground. That's its net vertical drop, and that turns out is what's most important for the energy analysis. Why? Because if I go back to my energy equation right here, look at this term and this term right here. Now, if I algebraically say move this term to the other side of the equation right here, I will have an mg times the quantity h naught minus h1. Do you agree with that? And once I have the h naught minus h1, here is an expression for h naught minus h1 right here. That's the net vertical drop. You can rewrite the h naught minus h1 in terms of the initial distance the block is from the spring, how far it compressed the spring, and the inclination angle of the incline. So the problem will all come together, and you can tie all the variables up that way.